Here is a combined summary of the 4 pages. This research paper proposes a nonlinear model predictive control (NMPC) framework that ensures continuous time constraint satisfaction and accurate evaluation of the running cost without compromising computational efficiency. The framework leverages the successive convexification approach for trajectory optimization, involving reformulation of path constraints and running costs by augmenting system dynamics, using multiple shooting for exact discretization, and solving the discretized receding-horizon optimal control problems with a convergence-guaranteed sequential convex programming (SCP) algorithm. The NMPC framework addresses limitations of existing algorithms, which are often limited to nonlinear dynamics with box constraints on the control input and do not guarantee continuous time constraint satisfaction. The proposed framework utilizes successive convexification, enabling continuous time constraint satisfaction and efficient problem solving. The authors demonstrate the effectiveness of the proposed NMPC framework through a numerical example with reference tracking and obstacle avoidance. The SCP algorithm is used to solve the reformulated problem, involving penalizing non-convex constraints and solving a sequence of convex subproblems. The authors use a prox-linear method to solve the penalized problem, which converges to a stationary point, also a KKT point if the converged point is feasible. Implementation details of the SCP algorithm include computation of gradients, numerical scaling, and preconditioning operations. The authors define performance metrics for SCP within an NMPC simulation, including linearization error, violation of path constraints, and overall convergence of the SCP. The NMPC framework recursively solves the receding-horizon optimal control problem, offering robustness against uncertainties and varying characteristics. The proposed approach provides a flexible and efficient way to solve optimal control problems with complex constraints and nonlinear dynamics, and can be easily customized and extended to solve various optimal control problems. Here is a combined summary of pages 58 of the research paper. The authors propose a novel nonlinear model predictive control (NMPC) framework that incorporates a sparse discretization grid to handle longer horizons while reducing computational complexity. The framework utilizes a reformulated optimal control problem that enables the selection of the number of node points based on the degrees of freedom required in the parameterized control input. The authors highlight the importance of considering the time interval between each NMPC run, denoted as increment TMPC, which is crucial for achieving rapid convergence and alleviating challenges related to ill-conditioned sensitivity matrices in stiff systems. To enhance computational efficiency, the authors propose a warm starting technique that allows the sequential convex programming (SCP) algorithm to converge to an acceptable solution within a limited number of iterations. The warm start solution is obtained by shifting the SCP solution from the previous time instant and integrating dynamics to determine the initialization for the states and control inputs at the last k nodes. The authors demonstrate the proposed NMPC framework for output reference tracking with obstacle avoidance for a double integrator with drag and bounded control inputs. They relax the boundary condition defined for CTCS to satisfy the linear independence constraint qualification (LICQ), and prove that for each relaxation parameter, there exists a constraint tightening value delta OBS such that the obstacle avoidance constraint is satisfied. The authors then present a successive convexification framework for nonlinear model predictive control (NMPC) problems, which involves reformulating the optimal control problem by embedding path constraints and the running cost into the dynamics function. This allows for the use of sparse discretization grids without encountering intersample constraint violations or a degradation in the accuracy of the running cost. The prox-linear method, a convergence-guaranteed successive convex programming (SCP) algorithm, is employed to solve the reformulated optimal control problem. The proposed framework is demonstrated on a tracking problem involving obstacle avoidance, and the results show that the node-only and CTCS formulations can successfully track the reference output while avoiding obstacles. The tracking error and obstacle avoidance constraint violation are presented in figures 4, which demonstrate the effectiveness of the proposed approach. The successive convexification framework offers the benefit of being able to operate in an RTI-like mode while achieving a favorable solution in a few iterations and maintaining real-time capability. The literature review encapsulates the state-of-the-art in model predictive control, (MPC), and related optimization techniques. It begins with seminal works on MPC, such as Main's, 1973, Differential Dynamic Programming, and Nosedal and Wright's, 2006, Numerical Optimization. The authors then delve into more recent studies, including sequential convex programming and generalized Gauss-Newton methods, Messerer et al. 2021, and robust output feedback control, Sodrodini and Tedrake, 2020. A range of applications are covered, including control of swarms of spacecraft, Morgan et al. 2014, wind turbines, Schlipf et al. 2012, and plug-in hybrid electric buses, Xie et al. 2019. Real-time algorithms for non-convex powered descent guidance, Reynolds et al. 2020, and successive convexification for 6 degree of freedom powered descent guidance, Schmuck et al. 2020, are also discussed. Optimization techniques are thoroughly explored, including multiple shooting, Kiranen et al. 2015a, and Pontryagins minimum principle-based MPC, Xie et al. 2019. The review also touches on control-limited differential dynamic programming, Tassa et al. 2014, and extrapolated proportional integral projected gradient methods for conic optimization, Yu et al. 2022a, 2022b. The importance of robustness and constraint satisfaction in MPC is emphasized, with references to robust dual-control MPC, Weiss and DiCarano, 2014, and real-time robust MPC, Zeilinger et al., 2014. Auto-generating microsecond solvers for nonlinear MPC, Kiranen et al., 2015b, and efficient optimal control packages, Sargent and Sullivan, 1978, are also highlighted. This comprehensive review provides an in-depth overview of the current state of MPC and related optimization techniques, showcasing key concepts, methodologies, and applications.